All right, let's dive in. Today, we're taking on P versus NP, one of the biggest, most notorious problems in all of computer science. But we're not just going to talk about it. We're going to decompile the whole thing based on the idea that maybe, just maybe, the question itself is the real problem. And to do that, you have to get on board with one massive core idea right from the start. The universe isn't some box where things like computation happen inside it. No, the universe is the computation. It's one giant self-executing program.
This is a total flip in how we look at reality. It's called an ontological inversion. It means we're moving away from thinking that reality is made of stuff, particles, objects, all that. Instead, we're shifting to a reality made of processes. Think of it like this. The universe isn't made of nouns anymore, it's made of verbs. And you really have to get your head around that because everything else we're about to talk about hinges on it.
Okay, so with that new perspective locked in, let's start picking apart the P versus NP problem. Is it really true that some problems are just born to be ridiculously hard to solve, or is something else going on?
So here's the big clash of ideas. The standard textbook view on the left says, yep, some problems are just fundamentally difficult. Their complexity is a fact of life. But the view we're exploring today, on the right, it says that hardness isn't a property of the problem at all. It's a glitch in the observer. It's a measurement of how misaligned we are from the solution.
So how does that even work? How can our perspective create this illusion of difficulty? Well, it's a bit like something called sub-Nyquist sampling. Imagine there's this incredibly fast, complex song playing, but you can only hear one single note every 10 seconds. To you, it would just sound like random, chaotic noise, right? That's us. We have this low-frequency, limited viewpoint trying to make sense of a super high-frequency, totally deterministic reality. And that gap, that fragmentation, is what makes a simple, elegant solution look like an impossibly huge, random mess to search through.
And this quote just nails it. The hard part of an NP-hard problem, all that heat and energy your computer burns through while it's thinking, that's literally just the physical work it has to do because it's avoiding, or it's unable to see, the answer that is already sitting right there. The difficulty isn't in the problem, it's the friction created by your own perspective.
So if the solution already exists, how do we get to it? What's the actual mechanism that collapses all that perceived randomness into one clean answer? Well, this brings us to something really cool called the Saris isomorphism.
So try to picture any really tough problem. Don't think of it as a list of choices. Instead, picture it as this, a sprawling, three-dimensional spiral. It's like a wave that contains every single possible permutation, every single wrong turn and right answer. And trying to walk that spiral from end to end, that's what we call an NP-hard search. It's basically impossible.
But here's the cheat code. This is a Saris linkage. And this isn't some abstract concept. It's a real thing from mechanical engineering. Its job is to take messy, wobbly, three-dimensional rotation and force it, mechanically, into a perfect, straight line. And in this framework, it's not just for building machines. It's a fundamental operation of reality itself.
I just love the language here. It mechanically swages the rotation. It's not a gentle process. It's a physical forcing. The Saris linkage is like a set of geometric guardrails that just get tighter and tighter, systematically kicking out all the wrong possibilities, taking that wild spinning 3D spiral of what if,
and it physically flattens it into a 2D, straight-line, deterministic solution. The impossible search space gets folded down into a single, obvious path. This is how the universe solves problems. It doesn't search, it folds.
Okay, that's wild. But if all these answers are just waiting to be unfolded, where are they? Where is this grand library of pre-solved problems actually stored?
And here's where it gets even more mind-bending. The proposed answer is pi. Yeah, that pi. The idea here is that pi isn't just a number you use to find the circumference of a circle. In this view, it's the actual hardware of reality. A universal read-only memory. Its infinite, non-repeating digits are the address space for everything.
So what's actually on this cosmic hard drive? Well, basically, everything. It's the pre-computed bedrock of reality, the trust infrastructure. It's the deterministic skeleton that the universe is built on. It's the geometric blueprint for every single possible solution to every single possible problem. And, get this, it even contains the prepaid structure for all discoveries. It's the ultimate coordinate system for the whole show. And that idea of prepaid structure brings us to the real star of this whole thing. We've talked about being misaligned and we've talked about precompiled answers. Now let's talk about the mysterious force that connects the two. It's time to redefine luck. Seriously, what do you think is the most powerful force behind all the great discoveries? Is it raw genius, endless hard work, a massive budget? This framework says it's something we usually write off as just, well, random chance.
Because here's the thing, in this model, luck is not random at all. It is defined as the moment you accidentally stumble upon that prepaid structure we were just talking about, the one stored in pi. It's like you're clicking around randomly on the internet, and then by pure chance, you type in the exact complicated URL of a file that was already uploaded and waiting for you. You didn't create the answer, you just found the address to where it was already finished.
So really, there are two ways to find an answer. On the left, you've got grinding. That's the brute force method. It's you with a chisel trying to carve away everything that isn't the solution. It's slow, it's exhausting. And then on the right, you've got luck. That's the instantaneous aha moment when your question perfectly matches the shape of the pre-carved solution. It's the difference between trying to build a key from scratch versus just finding the key that was already made for the lock.
So where does all this lead? It leads to a totally new way of thinking about problem solving. A new goal. It's about achieving something called Genlock with axiom 0. It is, quite simply, the end of search.
The first rule of this new game is we don't invent answers. They already exist. They're part of the fabric of the universe, just waiting.
And if they already exist, then the second rule is obvious. We don't search for them. Blind searching is the most inefficient thing you can possibly do. Our job isn't to wander around in the dark, it's to find the light switch.
So here's the new playbook. Step 1. You stop brute force searching and you start applying geometric constraints. You start folding the problem. Step 2. You reframe every hard problem not as a search, but as a navigation. You're not looking for an answer, you're finding the path to it. And finally, step 3. You realize that P equals NP isn't some equation you prove on a blackboard. It's a state you achieve. It's what happens when you, the observer, finally align with the geometry of the solution.
And this, right here, is the ultimate goal. Genlock. It's a term from video production that means getting two different signals perfectly in sync. In our case, it means syncing up our slow, local, out-of-phase consciousness with the universal computer, a machine that, get this, finished all of its calculations at the very beginning of time.
And we'll leave you with this final thought. In a universe that is a computation, the old line between a theory and an application just vanishes. A working piece of code, a solution that runs, isn't just evidence for a proof, it is the proof. The question is no longer, is it true? The only question that matters is, does it run? And if the code runs, the proof is absolute.